We are looking at reviewing, starting at the beginning of Chapter 8. We've talked about different types of variation. So before we start, what is the basic equation for direct variation? Y equals k times x, okay? And then inverse variation? Y equals k divided by x. Yes? Okay. So there's a process. It's a three-step process for these first few questions. You are being asked to write a function to model the situation. We are given some information in terms of an actual coordinate point or data. They're telling us x is -2 and y is 6. They are also giving us a statement in words that you need to translate before you try to dump any numbers in. I'm going to be looking for that translation. Generic, just with the variables, no numbers. So y varies inversely as x, or y varies inversely with x. We just said our inverse variation looks like this. Y equals k divided by x. So that's step 1. You're writing your basic format. Step 2 is to plug in your numbers. So we are told that y is 6 and x is -2. From that, we can find k. What is the value for k? Okay. All right, so that's step 2. Using the numbers, we figure out our k value. Step 3 is we now take that k value and we dump it back into our generic first step. So the model would be y equals -12 divided by x. Okay. Question 2. X is 6 and y is 9 when z is 12. Then it says z varies inversely with y and directly with the square of x. Okay, translating that. Z varies inversely means we're going to have something in the denominator, yes? Inversely with y, and directly means it's in the numerator, directly with the square of x, we would put that down as x squared. Okay, so we have our generic equation. Now we start dumping in our numbers. We said z was 12, x was 6, and y is 9. What is 6 squared? 36 divided by 9. So we have 12 equals k times 4. So k has to be 3. All right. Our last step then is to dump that back in. So the model would be z equals 3x squared divided by y. All right. The next couple examples, it says to determine if it is direct, inverse, or neither. If it is direct or inverse, they want you to come up with an equation for it. Okay? If it's neither, then you say neither, and you can't come up with an equation. So to do this, we want to figure out if there is some kind of constant. So let's look back here. We said direct variation was y equals k times x. What would that be if I solved it for k? Y divided by x equals k? Okay, so if I think it's a direct variation, then all my y coordinates divided by my x coordinates have to come out as a constant. So let's check on this first one. If I take y divided by x, so 6 divided by -2, -3 divided by 4, am I getting the same answer each time? Then it's not direct. Okay, let's look at the second example. If I take my y divided by x, I have 8 divided by 2, I have -20 divided by -5, 1 divided by 1/4. What am I getting each time? 4. So since I'm getting a 4 for all of these, that is my k value. So it does fit a direct variation problem. So I would say my type of variation is direct. We figured out that our constant of variation has to be 4. So my equation would be y equals 4 times x. If it's inverse variation, and we solve for k, then x times y has to come out constant. So let's go back and check the one that wasn't direct. What do we get if we take x times y? Multiplying our x's and y's together, we get what? -12 for all of them. So that means k has to be -12, and it is fitting that inverse type variation. So my equation then would be y equals -12 divided by x. Questions on that? All right, question 5. It says, using variation, describe how the variables in the given equation are related. So now instead of me giving you the words and you writing out the equation, we're doing the reverse. So if it starts out x equals, we would start out writing what? X varies. Okay? X varies. Now, there's several variables in here. Okay, so let's take it in pieces. X varies, how would we say for y? Directly, since the y is in the numerator. So x varies directly with y, and now inversely with multiple variables, right? W and z are both in the denominator. So we would say, and inversely with the product of w and z. Okay, we are multiplying the w and z together and putting those in the denominator. All right, any questions on variation?
So you don't say anything.
K is the constant of variation, so as soon as you say x varies or z varies, there's always going to be a constant in there. So no, you don't ever describe K. It's just by saying the word varies, there's going to be a K in there. All right, moving on. It says, write an equation for the translation of y equals 4 divided by x with the given asymptotes. This is an inverse variation problem, right? Y equals k divided by x. So when we looked at the shape of those, we had branches in quadrants 1 and 3, unless we had a negative k value, right? Then it flip-flopped and reflected over the x-axis and was in 2 and 4. We have a positive k value, so we know it's going to start out in quadrants 1 and 3. The 4 is going to do what to my graph compared to a 1? It does have a vertical stretch, so it's going to pull away from the origin a little bit. Okay? Now, it says we have the given asymptotes. So picture an asymptote at x equals 2. Okay, vertical asymptote at x equals 2. That tells me we shifted which way? We shifted right 2. Okay, then we have a horizontal asymptote at -3, which means we moved down 3, right? Because our asymptotes start out at the x and y axis. So we went right 2 and down 3. So what do we have to do to our equation here to show that we want it to go right 2? All right, agree with that? We put a negative with -2 with the x. It's going to move it right 2. All right, somebody else. How do we show that it moved down 3? Where? On the outside, yep, a minus 3. Okay? So if I give you the asymptotes, you can tell me how that equation shifted.
I was thinking x bars. Because how we did degrees.
Horizontal asymptotes are based on degrees, yes. But in this format, when it's in that transformation format, we can't analyze horizontal asymptotes using degree because you don't have a single fraction. Okay, that was a technique we used for the more complicated rational expressions that weren't in transformation format. Okay, like the ones we're getting to right now. So it's asking me to identify in these next couple any holes, horizontal or vertical asymptotes. In order to do this, we want to have things factored. So take a minute, anything that's not factored in 7, 8, or 9, go ahead and do that. All right, did you pull a 3x out? All right, so do we have any points of discontinuity? Points of discontinuity are any problems caused by variables in the denominator, right? They might be holes, they might be vertical asymptotes, they're just at this point problems for us. Do we have any problems? Yes. What value makes the denominator 0? Okay, we can't divide by a 0, right? So x can't be negative 3. We have to decide, is it a vertical asymptote or is it a hole? If it drops out, since we have an x plus 3 factor both in the numerator and denominator, we can get rid of it. That means x being negative 3 is it's removable, which means it's a hole. All right, so we would say there's a hole at negative 3 for x. Do you remember how we find the y coordinate of that hole? We plug it into the simplified version. So if we get rid of those x plus 3 factors, this really becomes y equals 3x, right? It's just a line. It's going to go through the origin, have a slope of 3, right? But our line is going to have a hole when x is negative 3. So if we plug a negative 3 in here, what do we get? All right. So we have a line that has a slope of 3, but there's one hole in that graph at the point negative 3, negative 9. Okay? Any vertical asymptotes? Do we have any other points of discontinuity that were non-removable? Okay? So you're going to say none, because if you leave it blank, you're going to get it wrong. It's going to make me think you didn't know if there was one or not. If you've analyzed it and said there isn't one, then you have to say there's none. Horizontal asymptotes. This is where we start looking at degree. If you look at the degree of the original equation, the top degree is 2, the bottom degree is 1. Top is bigger, okay? If I analyze the simplified version, top degree is 1, bottom degree is 0. There's no x's in the denominator. Top is still bigger than the bottom. If you analyze this, make sure that you are looking at the degree if that numerator was put back together, multiplied back together. Okay? Typically, this original version is going to be the easiest for analyzing degree. So, top is bigger, which means what happens when the numerator degree is bigger than the denominator? There isn't one. All right, so we're going to say none. When the top degree is bigger, there isn't one. All right. Next example. There's nothing to factor. Do we have any points of discontinuity? We have a problem when x is negative 2. Okay? So when x is negative 2, is it removable? Do we have an x plus 2 factor in the numerator? So it's not removable, which means it is a vertical asymptote. So we have a vertical asymptote at x equaling -2. We have no holes, since there was only that one point of discontinuity. How about for horizontal? Degrees are the same, right? They're both degree 1. So we move to the leading coefficients. All right? So degrees same, use leading coefficients. So in this case, our leading coefficient is 3 divided by 1. So y equals 3. Make sure that you are giving me asymptotes as equations and not just single numbers. Okay. Question 9. Already in factored form for you. Do we have any points of discontinuity? We actually have 2 of them. When x is -5, somebody else, x is 4. 2 points of discontinuity. Let's start with the -5. Is it removable? No. So that means it is a vertical asymptote. X equaling -5 is a vertical asymptote. Can we remove the issue with 4? Yes. The numerator has an x minus 4. The denominator has a 4 minus x. If we were to factor out a -1 from this, we'd have 4 minus x left, correct? So we can remove that, but it does leave a -1 in its spot. Okay? So we have a hole at x being 4. What does this simplify down to? Okay, so if we dump a 4 in there, we end up with -1/9 for the y-coordinate of our hole. All right, horizontal asymptotes. Now this one was already in factored form for us. I'm going to put it back the way it was. If we were to FOIL out that denominator, we'd end up with an x squared, correct? So I want you to think of this as being an x to the first in the numerator and an x squared something in the denominator. What happens when the top degree is smaller? So top degree smaller, we have one right on the x-axis at y equals 0. So make sure you know how to analyze degree, and you have 3 scenarios. If the top degree is smaller, we have one at 0. If the top degree is bigger, we don't have one. And if they are the same degree, we go to those leading coefficients. Okay? All right. Let's put it all together now. We need to find holes, vertical asymptotes, horizontal asymptotes. In addition to that, we were finding x and y intercepts. We were looking at maybe making a table and finding a few other points to plot. So our first one here is factored for us. We have points of discontinuity at x being -1 and x being 3. Okay, let's start with the -1. Is it removable? So it is a hole at -1. If we do remove it, this simplifies down to be what? Not 0, but 1 over x minus 3. Okay. That is now in transformation format. It's a basic 1 divided by x that's been shifted which way? Right 3. So can you picture it? The one thing that's different about this is that it has a hole where the original 1 divided by x minus 3 wouldn't. Okay? So because I had this extra piece in here, my graph is going to have a hole in it. compared to just a plain y equals 1 divided by x minus 3. Okay. If we put a negative 1 in here, what do we get for the y coordinate of our hole? Okay. Do we have any vertical asymptotes? Were there any non-removable points of discontinuity?
3.
All right, at 3. And then horizontal asymptotes. Top degree was, if you look at the original, top degree was 1, and the bottom degree was 2. So the top degree is smaller. If we look at our simplified version, that is still the case, because we would have x to the 0 for a numerator. So top degree would be 0, bottom degree would be 1. Top is still smaller. So we should have a horizontal asymptote at 0. So let's fill in what we know. Horizontal asymptote at 0, vertical asymptote at 3. And then we have a hole at -1, -1/4. All right, so that blue thing is a hole. Try to make yours look like a hole. Okay? So we should have a pretty good idea, right? We said this is a basic rational function, that reciprocal function 1 over x, that's been shifted to the right 3. But let's find a few more values to make sure our graph is accurate. We want to pick a couple x's on either side of that vertical asymptote. So I'm going to use 1 and 2. I can't use 3 because that's where my vertical asymptote is. And then 4 and 5. That'll give me a few different points on each side. We should also look to see if we can find any x or y intercepts. Those are really good points to find. How did we find x-intercepts? We put 0 in for y, which means we're looking at what makes the numerator 0. But our numerator is just a plain 1. There's no variable there. So is there any value that would turn that 1 into a 0? All right. So we're going to say in this case there's none for x-intercepts. Our y-intercept is what we get for y when we put a 0 in for x. So if we put a 0 in for x in our simplified version, 1 divided by 0 minus 3, -1/3. So we know that we're going to hit the y-axis at -1/3. And we know we're not going to hit the x-axis at all. All right, let's plug a 1 in. We're putting these all into that simplified version. Putting a 1 in for x, we get -1/2. Putting a 2 in for x, we get -1. Putting a 4 and putting a 5. All right, plotting some points. At 1, we are at -1/2. At 2, we are at -1. At 4, we are at 1. And at 5, we are at 1/2. So our graph should be coming down here, leveling off just above the x-axis. And then we have another branch here. It's going to go bypass that hole, right? And approach the two asymptotes. I would caution you, on your test, you will be asked to find all of this information: x-intercepts, y-intercepts, vertical and horizontal asymptotes, holes. Make sure that the graph you draw fits the information you've given me for all of those details. It's very common for students to say, there's a hole here, or there's a vertical asymptote, or there's an x-intercept, but your graph doesn't show that. All right? Make sure that it's matching. For this one, it is in transformation format. You cannot analyze horizontal asymptotes using degree unless you were to put this all back together as a single fraction. In other words, getting a common denominator under the k part, combining it all. If it is already in its transformation format, don't make it harder. You know which way it's moved. Your asymptotes used to be on the axes. Which way did we shift this? What is the 2 going to do? It's going to go to the right 2. So picture your vertical asymptote shifting to the right 2. What does that equation look like? X equals 2. Okay? What does the 3 on the end do? All right, we went up 3. So instead of being on the y-axis, we are going to be up 3. What's the equation of that horizontal asymptote? Okay. So in transformation format, take them right from where you're shifted, left, right, up, down. Okay? Do we have any other points of discontinuity? No. So we aren't going to have any holes. And even before we were to graph this, based on just the asymptotes, what would we say for domain? X cannot equal 2, and y cannot equal 3. Okay? X can't equal 2, y can't equal 3. If we were to graph without the transformation, y equals 1 divided by x, which quadrants are we in? One and 3, right? So let's pick a couple values. Let's do -2, -1, +1, +2. 1 divided by -2. It's -1/2. 1 divided by -1. It's -1. 1 divided by 1. 1 divided by 2. That's the parent function. Okay? So if we were to plot those points, -2, -1/2, -1, -1, we now have to shift them right 2 and up 3. Okay? If we plot the other two, 1, 1 and 2, 1/2, we now have to shift those right 2, up 3. Go ahead and do that to figure out where your new points should be. So we have our graph still in that general quadrant 1 and 3 kind of format, but we've just shifted it right and up. Okay? We're going to stop here for today. Tomorrow we will look at the second half of this review where we look at sections 4 through 6. Your homework is in a packet that I will be passing out to you. You guys are going to be doing the first page, both sides. All right, that's all of the stuff that we talked about today. If you know that tonight you have more time than you will tomorrow, feel free to start working on the second half of that. Okay?